Next up, our next mini seminar is on organ transplantation, and it will be given live by Jeroen Berrevoets, who is a PhD student who joined our lab last year. Jeroen, whenever you are ready, please go ahead and share your screen.
Okay, so I want to thank everyone for sticking around so long. I guess this means everyone's super interested in machine learning and organ transplantation. Rightly so, because it is a huge problem. So organ transplantation has the potential to have a massive impact on a patient. I borrowed some statistics from Statistica, which says that a heart transplantation in the US can cost over $1.6 million for one patient. Livers can cost over $800,000, and the list goes on. But other than money, it's also a matter of life and death. If a patient doesn't receive an organ, they will simply die. So we need to distribute as many organs as we can and try to come up with a good match for every organ and every patient on the wait list. So there is obviously huge potential. However, current allocation policies overly simplify the problem. So given this massive problem, existing policies such as MELD-NA and Transplant Benefit in the UK, they grossly simplify it. For instance, MELD-NA only uses 4 patient biomarkers and 0 organ biomarkers to distribute an organ, which is clearly inefficient. The UK does a little bit better, but they estimate the net benefit from an organ using linear and biased methods. And having a hugely complex space such as the organ transplantation space, linearity is obviously not a good idea. The lab has been active in this area since 7 years, before Mihaela came to the UK, actually. So there is a lot of research going on in the lab on organ transplantation, and we wrote this spotlight on organ transplantation on our website, which I linked here. However, with our recent papers, we really pushed beyond any of the previous endeavors using deep learning methods, causality, and even queuing theory. We push the boundaries of both the ML as well as the clinical world in organ transplantation. So I mentioned causality. We use causality to answer one of 3 pressing questions in organ transplantation. And the first is, how long would this patient live without a donor organ? So we do observe transplantations with a given patient, but we don't observe what would have happened if they didn't receive an organ. Alicia presented earlier what CATE could do to this problem, but this is not a standard CATE problem at all. This sounds like a CATE problem because there is a treatment being the organ, there is a condition being the patient, and there is a causal question, but it's much more complex than that. Organs are unique. Not one treatment is the same, so we cannot compare subpopulations. If we transplant a donor organ into one patient, we will never see the same organ twice, nor will we see the same patient twice. So we have to infer beyond just one treatment. We cannot use standard CATE techniques to solve this problem because usually they're defined as a binary treatment problem, categorical at most. And there are some methods from our lab actually that do this in a continuous space, but never for unique treatment. So a second question is this the best we may expect? So a patient has a limited time on the wait list before they die. There are only a limited amount of patients, and there is only one organ at a time. So given this organ that's available, can we expect a better organ in the future, or should we transplant this one for some patient? While some patients may be helped with a variety of organ types, others may only be helped with one type. And a typical example is if you have a high BMI patient, they can be helped with both high BMI and low BMI donors. But this is not true for low BMI patients. If you have a very skinny patient, we cannot give them a fatty liver, for example, because they would go in shock. We need to take into account the scarcity of a patient's ideal organ. And the third and last question is, what makes an organ allocation policy any good? How do we really evaluate it? Perhaps we should evaluate on patient outcome. We could also evaluate on most organs put to use, so less waste, or we could evaluate on the amount of years gained. We use a total population life years, which is what the UK uses as its evaluation, meaning we want to optimize the time the patient lives both before as well as after transplantation. So patients on the wait list are included in our objective. A first solution to this, which Alihan mentioned previously, is OrganNight, where we take in 3 different estimates and use them to weight which organ we should transplant into which patient. A first estimate is how well the patient matches with the available organ. So that would be patient features indicated in green on the figure. A second is how much net gain we may expect after transplantation. So how much months or years could the patient be expected to live if we give the organ, which is illustrated in purple. And then how rare is the patient's optimal organ, which is indicated in red. I have indicated on the figure how other allocation policies would allocate the available organ. For instance, incremental survival and best match would give it to a purple organ above, whereas organ night as the only one would give it to the lowest patient on the wait list, the most below, the blue one. Because it has a good balance of how much time they may expect to live, how much months the organ will give them, and how rare the ideal organ for this patient really is. Each estimate is based on past data on transplantation. So for the UK, we use 25 years of organ transplantation. We also use US data, which has over 20 years also on liver transplantation data. A second solution, which we also modeled in our lab, is called organ sync. An organ sync consists of roughly 5 steps. So the first step is to map the patient and organ space into a linear representation space using a nonlinear method. The second step is to build a new synthetic patient and organ pair to which we can compare to see what would have happened if we didn't give them an organ or give them some other organ. Using this synthetic patient, we arrive at step 3 and 4, where we estimate the survival time of the patient and place them on a queue, where each queue is associated with an organ type. Given these queues, we just distribute the organ to whatever queue is associated with the organ, and the next in line will give it. Priority is then based on the survival time or estimated survival time of each patient. So I'm going to share with you some results. Yes, prediction is very good. We have lower errors using organ sync or organ night, and that's very nice for a machine learning community. But the real meat is in this, where given some simulations, we can actually add life years to the patients using our method. Recall that our method does not introduce new transplantation techniques, new medicine. It's just a way to distribute organs differently. And by doing this well and correctly, we can actually add life years to people. The next steps we think are very crucial is we want to really change policy with these methods. So using or collaborating with 2 noteworthy clinicians in organ transplantation, both in the UK and the US, we want to change policy in, well, for starters, I guess, the UK and US, and to use these new machine learning methods to allocate organs better as we have previously. Thank you for your attention.